In the vast expanse of the cosmos, humans have always been drawn to explore the unknown, and at the heart of this remarkable journey lies the evolution of rockets. In human history, few inventions have shaped our destiny as profoundly as these fiery engines of exploration. These incredible inventions that rise through the sky and propel humans into outer space have been with us for over 2,000 years. Our journey through the evolution of rockets spans millennia, from the ancient Chinese fireworks that first ignited our fascination, to the thrilling possibilities of interstellar travel that lie ahead. Let's go back to a time when rocketry was nothing more than a distant idea. Inspired by fireworks, early Chinese philosophers and alchemists unintentionally started the journey of rocket technology. Their basic rockets, powered by solid fuel, marked the humble beginnings of this technology. And this is how it all started. Boötes was a brilliant Greek philosopher, mathematician, and astronomer who lived from 428 to 347 BC. Boötes, renowned for his inventive nature, is acknowledged for creating a unique invention, a small bird-shaped device. This remarkable bird was propelled not by feathers, but by a powerful jet of steam or compressed air. Suspended by a wire or mounted on a revolving bar, it rose in the skies. Boötes' creation marked the idea of rocket propulsion, a feat that would echo through the ages. Fast forward to a different era, around AD 10 to 70, and we meet the hero of Alexandria. Though not a rocket in the conventional sense, Hero's invention embodied the fundamental principles of rocket and jet propulsion. His steam engine, a marvel of ancient engineering, captivated the imagination. It featured a copper vessel heated by a fire below, causing water within to transform into steam. The steam ascended through two tubes, reaching a hollow sphere that spun freely. Ingeniously designed L-shaped tubes allowed the steam to escape in a burst of gas, propelling the sphere in the opposite direction. Hero's engine was a source of amusement, a toy that foreshadowed the potential yet to be realized. In the year AD 1232, a significant chapter in rocketry's tale unfolded on the other side of the world, the birth of Chinese fire arrows. These remarkable arrows, adorned with fire-breathing payloads, brought forth a new era of incendiary warfare. Pioneered by the Chinese, these ingenious devices used the explosive power of gunpowder to propel projectiles with incredible force and precision. These early innovations, from Boötes' soaring bird to Hero's spinning sphere, and the fiery brilliance of Chinese fire arrows, laid the foundation for the future of rocketry. However, the beginnings of gunpowder are shrouded in ancient history. We might not have all the exact details, but historical clues point to the Chinese discovering a basic version of gunpowder way back in the 1st century. This special mixture was made up of 3 simple ingredients: saltpeter, sulfur, and charcoal dust. When they set it on fire, it created dazzling sparks and wisps of smoke, like a magical fireworks show lighting up the night sky. But people in ancient China took this discovery a step further. They created thin tubes using bamboo and leather, sealed them at one end, and carefully filled them with this gunpowder mix. The real magic happened when they lit the powder. Depending on how tightly they packed it and the size of the opening, they could make either a mesmerizing spark fountain or a big, loud bang. Some of these early fireworks even had a habit of darting around unpredictably, pushed by the gases rushing out of their open ends. And this is where the idea of rockets started to take shape. By the year 1232, in the heat of battle during the confrontation with Mongol invaders at the Battle of Kaikeng, these primitive rockets found a new purpose. They were affixed to arrows, transforming them into fearsome weapons of war. In a monumentous clash, these rocket-enhanced arrows repelled the invaders, marking a pivotal moment in the history of rocketry. As time moved forward, so did our understanding of gunpowder's potential. Roger Bacon was a monk whose ideas echoed through the ages. In a book he wrote between 1214 and 1292, Bacon delved into the mysteries of gunpowder. He was amazed by what it could do. He said, "We can, with saltpeter and other substances, compose artificially a fire that can be launched over long distances. By only using a very small quantity of this material, much light can be created, accompanied by a horrible fracas. It is possible with it to destroy a town or an army." Bacon realized that even a tiny bit of this stuff could create a super bright light and a really loud noise. This newfound knowledge revealed its destructive power. You could use it to wipe out whole towns or armies. Legend has it that Wan Hu yearned for the stars and set out to construct something unique. He made a simple chair and attached 47 rockets powered by gunpowder to its legs. In some versions of this incredible story, Wan Hu's chair even had kite-like wings. On the day of the big launch, 47 brave helpers rushed forward and lit the fuses of all those rockets at the same time. What happened next? An incredibly loud explosion echoed through the sky. And when all of the smoke cleared, guess what? Wan Hu had disappeared. Some people believe he might have actually gone into space and become the legendary man on the moon. Regardless of what really happened, Wan Hu had an innovative idea: to use rockets to travel among the stars. For centuries to come, rockets and cannons vied for supremacy as the weapon of choice on the battlefield. Technological innovations shifted the balance back and forth as each system had its own strengths. Cannons were known for their accuracy, while rockets offered rapid fire. The introduction of breech-loading cannons accelerated the firing process, while rocket fins enhanced accuracy. Cannons boasted greater range, yet rockets could reach remarkable distances. The competition was fierce, and inventors continued to push the boundaries. The evolution of rocketry was marked by a relentless motivation for innovation. With each passing era, inventors sought to improve rockets, making them more reliable, accurate, and powerful. These advancements weren't just about warfare. They were laying the foundation for something much greater: the journey into the cosmos itself. In the year 1420, an Italian inventor named Johannes de Fontana made a groundbreaking discovery: a surface-running rocket torpedo. It was designed with a mission to set enemy ships ablaze. Imagine a rocket that could skim across the water, carrying the potential to unleash devastating fire upon seafaring foes. This was a glimpse into the early days of rocket warfare. Fast forward to the 17th century, where we meet Kazimierz Siemianowicz, a Polish-Lithuanian commander who left an indelible mark on the worlds of artillery and rocketry. Siemianowicz was a true master of his craft, and his groundbreaking ideas would go on to shape the future of rocket technology. In his lifetime, Siemianowicz penned a manuscript titled Artis Magnae Artilleriae Pars Prima, which became a monumental work in the world of rocketry. One of his most revolutionary concepts introduced in this manuscript was the multi-stage rocket. This ingenious idea would later become the foundation for rocket technology, enabling us to explore far beyond the confines of our planet. Siemianowicz also proposed the use of battery-powered systems for launching military rockets, a concept far ahead of his time. This forward-looking idea would eventually pave the way for more efficient and powerful rocket propulsion systems, helping us reach greater heights in space exploration. Another remarkable innovation put forth by Siemianowicz was the suggestion of using delta-wing stabilizers to replace the traditional guiding rods. This innovation aimed to enhance the control and stability of rockets during flight. While it may seem commonplace today, back in the 17th century, this idea was nothing short of revolutionary, showcasing Siemianowicz's exceptional insight into rocketry. However, Siemianowicz's journey in pursuit of knowledge and progress was not without its challenges and controversies. Rumors swirled around him, suggesting that his relentless quest for understanding and innovation may have played a role in his untimely demise. Some clandestine guilds, fiercely protective of their rocketry secrets, were rumored to have opposed Siemianowicz's work and sought to silence him, even going as far as attempting to suppress his manuscript. Our journey continues with a name well known to many: Galileo. He was an Italian astronomer and mathematician born in 1564. Galileo was not just an observer of the heavens. He rekindled the spirit of scientific experimentation and challenged established beliefs about mass and gravity. One of his groundbreaking contributions was the concept of inertia, the idea that an object in motion tends to stay in motion unless acted upon by an external force. It set the stage for later discoveries by Sir Isaac Newton, who came up with the laws of motion. Inertia became a cornerstone of our understanding of how objects move in the universe. Sir Isaac Newton, a renowned English scientist born in 1642, is celebrated for his exceptional contributions to science and engineering. These laws, explained in his famous work, Philosophiae Naturalis Principia Mathematica, served as the foundation of rocket science and made complex concepts accessible to a wider audience. Newton's groundbreaking work in physics not only marked a significant achievement, but also left a lasting legacy in the world of science. His laws of motion, outlined with great clarity and precision in his seminal work, provided valuable insights into the fundamental principles governing the movement of objects in our universe. Newton's first law, known as the law of inertia, established that an object remains at rest or in uniform motion unless an external force acts upon it. In the context of rocketry, this law emphasized the need to overcome Earth's gravitational pull to initiate a rocket's ascent, requiring a substantial amount of energy. Newton's second law, equally crucial in rocket science, presented a mathematical framework for understanding how forces propel objects in space. This law states that an object's acceleration is directly proportional to the net force applied to it and inversely proportional to its mass. In practical terms, it means that a rocket's ability to accelerate and overcome gravity depends on the thrust generated by its engines and the rocket's mass. Engineers and scientists have used this law to design rockets with the necessary power-to-weight ratios to achieve escape velocity and reach orbit. The third law of motion, often referred to as action and reaction, has significant implications for rocket propulsion. Newton explained that for every action, there is an equal and opposite reaction. This principle results in the expulsion of exhaust gases at high speeds from the rocket's engines, creating a force that propels the rocket in the opposite direction. This law underscores a fundamental concept of rocketry. By expelling mass at high velocities, rockets can achieve propulsion in the vacuum of space, where there is no atmosphere to push against. Fast forward to the late 18th century, and we meet Colonel William Congreve. After British forces faced spectacular rocket barrages from the armies of Tipu Sultan in India, Congreve took charge of the British military rocket companies. Some of his designs were incredible, reaching distances of up to 6,000 yards. But it's not just about how far they went, it's about what they did. Congreve created rockets that were like fiery shotgun blasts, spraying the enemy with carbine balls. He also came up with incendiary rockets that set ships and buildings ablaze. And guess what? He figured out how to launch rockets from ships, which was a game changer. The famous phrase, "by the rocket's red glare," coined by Francis Scott Key during the War of 1812, was all about the British launching Congreve rockets. Just imagine the sky lighting up with those rockets. Now let's put these ideas into action. Newton's laws told us how rockets move, and Congreve's rockets showed us what they could do. To launch a rocket, first, a powerful engine is needed to overcome its initial inertia. The rocket's fuel burns, expelling gas, which propels it forward. This action generates an equal and opposite reaction, pushing the rocket upward into the sky. But even then, the idea of space travel was just a distant idea. It was Jules Verne who gave this dream wings with his novel De la Terre à la Lune. In this story, Verne envisioned a colossal cannon that would launch a manned projectile toward the moon. While this wasn't a rocket in the traditional sense, it had intriguing parallels with the future Apollo moon program. The projectile, known as the Columbiad, carried a crew of 3 and was fired at the moon from Florida. Now fast forward to the historic Apollo 11 mission, where the capsule was named Columbia, also had a crew of 3, and launched from Florida. Verne even correctly described how the crew would feel weightless during their voyage, although surviving the initial acceleration of the cannon firing would have been impossible. Jules Verne, an early visionary of space exploration, ignited the imaginations of countless future rocketeers and astronauts. As we continue our journey, we encounter a true pioneer of rocket science, Konstantin E. Tsiolkovsky. Born in 1857, Tsiolkovsky was not just a teacher and a theorist, he was a true aeronautics visionary. Hailing from a family of Polish descent who had settled in Russia, he wrote extensively and taught about the possibilities of human space travel. He is often hailed as the father of cosmonautics and human spaceflight. Tsiolkovsky championed the use of liquid propellant rocket engines, paving the way for rockets as we know them today. He also envisioned the concept of orbital space stations, a dream that would later become reality with space stations like the International Space Station. Tsiolkovsky was ahead of his time, advocating the use of solar energy and the colonization of our solar system. His groundbreaking work, Research into Interplanetary Space by Means of Rocket Power, was published in 1903, the same year the Wright brothers achieved powered and controlled airplane flight. In this work, Tsiolkovsky introduced the rocket equation, a vital formula that relates rocket engine exhaust velocity to the change in velocity of the vehicle itself, a cornerstone of rocket science. Meet Robert H. Goddard, an American college professor and scientist. In 1926, he built and flew the world's first liquid propellant rocket. Now, this rocket may not have reached the stars, but it did something extraordinary. It marked the beginning of a new era in rocketry. Climbing just 12.5 meters into the sky, it was a humble start, but it paved the way for the mighty Saturn V moon rocket that would launch humans to the moon 43 years later. At the request of local people, Goddard moved his experiments from Auburn, Massachusetts, to the deserts around Roswell, New Mexico. There, he continued to push the boundaries of rocketry. He developed a gyroscope system to control rockets in flight, created instrumentation payload compartments, and even worked on parachute recovery systems. That's why he's often called the father of modern rocketry. Hermann Oberth was a Romanian-born German. Oberth was captivated by the works of Jules Verne, and his passion led him to dedicate his life to the promotion of space travel. His dissertation for the University of Heidelberg, while initially rejected for being too imaginative, became the foundation for his groundbreaking book, Die Rakete zu den Planetenraumen, or Rocket to Space. In this book, he delved into the mathematics of spaceflight and proposed practical rocket designs and space stations. His visionary writings ignited the imaginations of a generation of rocket enthusiasts. Around the world, rocket societies sprang up, and Oberth's influence even played a role in the development of the V-2 rocket. As we move forward to the early 20th century, the world saw a surge in amateur rocketeers and scientists. They were dreamers who dared to use rockets in unconventional ways. They attached rockets to airplanes, racing cars, boats, and even bicycles with wings. They used them to create throw lines for rescuing sailors from sinking ships and to deliver mail to offshore islands. These daring experiments didn't always succeed, but they taught these visionaries how to make rockets more powerful and reliable. Then came World War II, a time of great upheaval and technological advancement. Rockets, once considered novelties and dream machines, transformed into powerful weapons of war. Overnight, they became a force to be reckoned with. Rockets powered nearly unstoppable German fighter planes and carried Japanese kamikaze pilots with bombs into enemy ships. The face of warfare changed forever. London, a city that had withstood the relentless onslaught of the Blitz, was about to face a new terror from the skies. In the late 1930s, with the German Verein für Raumschifffahrt, a society evolved into a team of brilliant minds. Under the leadership of Wernher von Braun, they crafted a rocket that was a technological marvel for its time. The V-2. This rocket ran on alcohol and liquid oxygen, boasting a range of 200 miles and reaching a maximum altitude of 55 miles. It had the capability to deliver a 1-ton explosive warhead to London without warning. Thousands of V-2 rockets were produced, but they came too late in World War II to alter the course of history. This rocket rained down on London, causing unimaginable destruction and panic among the civilian population. The V-2 rocket attacks on London during World War II were a terrifying and destructive chapter in the history of warfare. The rocket's speed and unpredictability made it nearly impossible to defend against. The attacks caused widespread panic, and the psychological toll on the civilian population was immense. In the midst of the Allied invasion of Normandy, the V-2 rockets created chaos and disrupted supply lines. The skies above Normandy became a battleground where rockets dueled with airplanes. The Normandy landings, also known as D-Day, were a pivotal moment in World War II. The Allies faced not only fierce ground resistance, but also the threat of V-2 rocket attacks. These rockets disrupted the logistical efforts of the Allies and added an element of uncertainty to an already perilous mission. The Allies knew that they had to act swiftly. The clock was ticking, and the world watched in suspense. Behind the scenes, a high-stakes game of espionage and intrigue was being played out. Intelligence agencies from both sides of the conflict raced to uncover the secrets of the V-2 program. Sabotage missions were launched to cripple the production of V-2 rockets, and scientists risked their lives to gather critical data. The race to understand and counter the V-2 threat was not limited to the battlefield. Intelligence agencies, including the British MI6, undertook daring operations to gather information on the V-2 program. Agents infiltrated German facilities and worked to sabotage the production of the rockets. The rocket had become a symbol of power and fear, and its control meant victory in a war that had engulfed the globe. Wernher von Braun, the brilliant mind behind the V-2 rocket, found himself at the center of a new race, the space race. The United States and the Soviet Union sought his expertise to conquer the final frontier. Wernher von Braun's journey from Nazi rocket scientist to American space pioneer was a remarkable chapter in the history of science and technology. His work laid the foundation for the United States space program, and he played a key role in the development of NASA. As World War II concluded in Europe, something remarkable happened. 300 trainloads of V-2 rockets and parts, along with the principal designers who chose to surrender to American troops, were transported to the United States. This marked the birth of the Intercontinental Ballistic Missile Development Program and laid the foundation for the future of space exploration. In a groundbreaking moment, a captured V-2 rocket, combined with a WAC Corporal rocket named after the Women's Army Corps, ushered in the era of two-stage rockets. The bumper whack took flight on May 13, 1948, marking the largest two-stage rocket launch in the United States at the time. It eventually reached an astounding altitude of nearly 400 kilometers, 250 miles, setting the stage for what was to come. The post-World War II era saw a race for supremacy in space between the United States and the Soviet Union. It was the Soviet Union that claimed the first victory on October 4, 1957, with the launch of Sputnik 1, a spherical satellite adorned with 4 antennas. Weighing 83.6 kilograms, 184.3 pounds, it marked a historic moment. Just 2 months later, Sputnik 2 followed, carrying a living passenger, a small dog named Laika. Though Laika didn't survive the journey, her mission paved the way for human space exploration. The United States entered the satellite race on January 31, 1958, with the triumphant launch of Explorer 1. Riding atop the Juno 1, a modified Jupiter C booster, this satellite, though much smaller than the Sputniks, weighed only 13.93 kilograms, 30.66 pounds. Explorer 1, equipped with a Geiger counter, made a groundbreaking discovery about the space environment. It detected what would later be known as the Van Allen radiation belts. In the late 1950s and throughout the 1960s, the X-15 experimental aircraft, a rocket-powered wonder, soared to the very edge of space. In a series of 199 awe-inspiring flights, this air-launched rocket plane shattered records. It blazed through the skies at mind-boggling speeds, reaching a staggering 7,274 kilometers per hour. 4,520 miles per hour. The X-15 also touched the heavens, ascending to an altitude of 108 kilometers, 67 miles. These daring test flights unveiled crucial insights into controlling spacecraft in space and mastering the delicate art of re-entry. Notably, among the elite roster of X-15 pilots was Neil Armstrong, the first American to set foot on the moon. On April 12, 1961, a historic moment unfolded as cosmonaut Yuri Gagarin embarked on a journey that thrust humans into the realm of space. Gagarin's spaceflight, lasting a mere 1 hour and 48 minutes, was a triumph for humanity. Within his Vostok 1 space capsule, he circled Earth once, soaring to an astonishing altitude of 315 kilometers, 196 miles. As his capsule re-entered the Earth's atmosphere, Gagarin demonstrated incredible courage by ejecting himself at an altitude of 6,100 meters, 20,000 feet, and safely parachuting back to the ground. Just weeks after Gagarin's historic flight, another pioneer emerged. American astronaut Alan Shepard embarked on a monumental journey inside his Freedom 7 Mercury space capsule. Perched atop a Redstone rocket, Shepard's suborbital flight marked a crucial milestone. While he didn't achieve full orbit, he reached an impressive altitude of 187 kilometers, 116 miles. His capsule gracefully returned to Earth, splashing down in the ocean just 15 minutes and 22 seconds after liftoff. It was in the wake of Alan Shepard's courageous flight that a bold challenge was issued. President John F. Kennedy, in a historic address to Congress, set forth an audacious goal: to send an American to the moon and bring them safely back home before the decade's end. This visionary proclamation shook the world. Unbeknownst to many, NASA had already embarked on the journey to make this dream a reality. They were crafting the components of a rocket that would become legendary, the Saturn V, towering at an astounding 110.6 meters, 363 feet. The Saturn V would dwarf all previous rockets. It would consist of 3 powerful stages, a capsule equipped with a propulsion unit for the return trip, and a 2-stage lunar lander. These remarkable milestones were the seeds of an incredible lunar odyssey. On February 20th, 1962, a momentous day dawned as astronaut John H. Glenn Jr. embarked on a historic journey into the cosmos. Riding atop the mighty Atlas missile, Glenn achieved a milestone that brought the United States on par with the Soviet space program. Glenn's mission was to orbit Earth, a feat he accomplished 3 times over, spending a grand total of 4 hours and 55 minutes in space. A sensor glitch prematurely signaled his return, suggesting a loose heat shield on his Mercury capsule. However, further examination revealed the shield was securely in place all along. It was a faulty sensor that caused the alarm. With Gordon Cooper's mission on May 15, 1963, the curtain fell on the Mercury mission. Cooper, a stalwart astronaut, remained in space for nearly a day and a half. The Mercury program had fulfilled its mission, paving the way for what lay ahead, the audacious journey to the moon. Project Gemini was a groundbreaking endeavor that followed in the footsteps of Mercury. The Gemini space capsule, perched atop a formidable Titan missile, accommodated not one but 2 astronauts. These missions, some lasting up to 14 days, served as laboratories for pioneering feats such as spacewalking, spacecraft rendezvous, and docking procedures. These were not just experiments, they were crucial evaluations of spacecraft systems essential for future lunar endeavors. Behind these remarkable achievements stood the Titan rocket, originally designed as an intercontinental ballistic missile. Yet its destiny reached far beyond Earth's atmosphere. In the 1970s, the Titan rocket carried the Viking spacecraft on its voyage to Mars and propelled the Voyager spacecraft toward the distant reaches of our solar system. Dr. Wernher von Braun was born in 1912 in Wöritz, Germany. His fascination with rockets and space exploration began at an early age when he read the works of German rocket pioneer Hermann Oberth. Young von Braun was drawn to the idea of space travel and dreamed of making it a reality. This dream led him to pursue a degree in mechanical engineering and later a PhD in physics. Von Braun's early career was marked by his work on the development of rocket technology for Nazi Germany during World War II. He was a key figure in the development of the V-2 rocket, the world's first long-range guided ballistic missile. Although this was a period marred by the use of his creations as weapons of war, von Braun's vision extended far beyond military applications. He saw rockets as a means to explore the cosmos and ultimately reach other celestial bodies. After the war, von Braun and his team of German scientists were brought to the United States as part of Operation Paperclip, a program aimed at harnessing German scientific expertise. This move provided von Braun with the opportunity to pursue his lifelong dream of space exploration on a grand scale. Von Braun's crowning achievement came in the form of the Saturn V rocket. He became the chief architect and engineer of this colossal vehicle, which would eventually carry astronauts to the lunar surface during the Apollo missions. The Saturn V was a technological marvel, a testament to human engineering and ambition. Standing at over 363 feet tall and weighing more than 6 million pounds, it remains one of the most powerful rockets ever built. Beyond his engineering prowess, von Braun possessed the ability to communicate his vision effectively. He wrote extensively on the subject of space exploration and collaborated with Walt Disney on the Tomorrowland TV series, which reached a wide audience and ignited the imaginations of countless aspiring scientists and astronauts. His words and vision set the stage for a new generation eager to explore the cosmos, making space travel a tangible and tantalizing dream. While Dr. Wernher von Braun's influence was firmly rooted in the realm of engineering and rocket science, Gene Roddenberry, born in 1921, embarked on a different journey. One guided by storytelling and a profound belief in the power of human potential. Roddenberry's early career took him to the skies as a distinguished World War II bomber pilot and later as a commercial aviator. These experiences gave him a unique perspective on humanity's relationship with technology and exploration. Roddenberry's foray into storytelling began with stories of the skies, but his imagination soon soared to the stars. He conceived the idea of a Western series set in a futuristic spacefaring society. This concept eventually materialized as Star Trek, a groundbreaking television series that premiered in 1966 and ran for 3 transformative years. Star Trek was more than just a science fiction show. It was a mirror held up to society, reflecting its strengths, weaknesses, and potential. The series boldly went where no show had gone before, not only exploring the uncharted depths of space, but also delving into a rich tapestry of scientific and social issues. It tackled themes such as diversity, diplomacy, ethics, and the exploration of the unknown, all within the framework of a futuristic utopian vision of humanity. The impact of Star Trek was immeasurable, transcending the confines of television screens and embedding itself in the cultural fabric. The show garnered a dedicated fanbase known as Trekkies or Trekkers, who found inspiration in its hopeful vision of the future. The crew of the Starship Enterprise, led by Captain James T. Kirk, became iconic figures in popular culture. Perhaps one of the most profound ways in which Star Trek influenced space exploration was through its association with the real-world space program. The first Space Shuttle orbiter test vehicle was aptly named Enterprise, a tribute to the fictional starship that had captured the hearts and minds of millions. This symbolic gesture underscored the show's impact on inspiring future generations of scientists, engineers, and astronauts. Gene Roddenberry's legacy extended far beyond the television screen. His storytelling not only entertained, but also encouraged people to envision a future of cooperation, exploration, and discovery. The enduring appeal of Star Trek led to numerous spin-off series, movies, books, and conventions, creating a vast universe of imagination for fans to explore. On the unforgettable night of July 20th, 1969, at 10:56 p.m. Eastern Daylight Time (EDT), an extraordinary event unfolded that captivated the imagination of people all around the world: the Apollo 11 mission. This daring mission marked the first time humans would set foot on the moon, a celestial body that had long fascinated humanity. The Apollo 11 mission was the result of years of scientific progress, technological innovation, and ambition. It was part of NASA's larger Apollo program, which aimed to send astronauts to the moon and bring them safely back to Earth. One of the key figures behind this audacious goal was President John F. Kennedy, who in 1961 boldly declared, "I believe that this nation should commit itself to achieving the goal before this decade is out, of landing a man on the moon and returning him safely to the Earth." This statement set in motion the ambitious Apollo program. Apollo 11 was led by astronaut Neil Armstrong, who would become the first human to set foot on the moon. Joining him were astronaut Edwin Buzz Aldrin and astronaut Michael Collins. Armstrong and Aldrin would descend to the lunar surface, while Collins would remain in lunar orbit, guiding the command module. On July 16, 1969, the world watched in awe as Apollo 11 lifted off from Kennedy Space Center in Florida. The Saturn V rocket, one of the most powerful ever built, propelled the spacecraft into space. The launch was a resounding success, and the crew began their journey towards the moon. The journey to the moon was a meticulously planned one, lasting several days. It involved a series of carefully calculated maneuvers and course corrections to ensure the spacecraft followed the correct path. The crew relied on precise calculations and constant communication with mission control on Earth. After traveling for approximately 3 days, Apollo 11 entered lunar orbit. Michael Collins remained in the command module, orbiting the moon, while Neil Armstrong and Buzz Aldrin prepared for their descent to the lunar surface. On July 20th, 1969, the lunar module, named Eagle, separated from the command module and began its descent towards the moon's surface. It was a tense moment as Armstrong and Aldrin skillfully guided the Eagle through a series of maneuvers to land safely. As the world held its breath, Neil Armstrong descended the ladder of the lunar module and took that historic step onto the moon's surface, proclaiming, "That's one small step for man, one giant leap for mankind." Buzz Aldrin followed shortly after, and the two astronauts became the first humans to walk on another celestial body. Armstrong and Aldrin spent approximately 2.5 hours on the lunar surface, conducting experiments, collecting samples, and taking iconic photographs. They also planted the American flag as a symbol of their achievement, symbolizing the spirit of exploration and human accomplishment. After their successful lunar exploration, Armstrong and Aldrin rejoined Michael Collins in the command module. The spacecraft then began its journey back to Earth. The re-entry and splashdown in the Pacific Ocean on July 24, 1969, marked the conclusion of their historic mission. The Apollo 11 mission continues to inspire generations, reminding us of the limitless potential of human endeavor. Neil Armstrong's words as he stepped onto the moon still resonate today, urging us to dream big and reach for the stars.
It's one small step for man, one giant leap for mankind.
That's one small step for man, one giant leap for mankind, represents a milestone in human history, reminding us of the boundless possibilities of science, exploration, and the human spirit. The Saturn V rocket, a colossal engineering marvel, played a pivotal role in the Apollo 11 mission's success. Standing at 363 feet, 111 meters tall, it was comprised of three main stages. The first stage, powered by 5 F-1 engines, provided the initial thrust needed to escape Earth's gravity. The second stage, with 5 J-2 engines, continued the journey to space. Finally, the third stage, housing the single J-2 engine, propelled the spacecraft into lunar orbit. The lunar module Eagle had two parts, the descent stage and the ascent stage. The descent stage served as the landing gear on the moon, equipped with landing pads and rocket engines to facilitate a gentle landing. The ascent stage contained the engines necessary for the lunar liftoff, allowing the astronauts to rendezvous with the command module in lunar orbit. On the lunar surface, Armstrong and Aldrin conducted a series of experiments and collected rock and soil samples. They deployed scientific instruments, including a seismometer to study moonquakes, a solar wind experiment, and a laser-ranging retroreflector to measure the Earth-Moon distance accurately. The astronauts also documented their activities, capturing breathtaking photographs of the lunar landscape. They left behind a plaque that read, "Here, men from the planet Earth first set foot upon the moon, July 1969 AD. We came in peace for all mankind." As we transition from lunar missions, we arrive at a new chapter of space exploration, a place we call Skylab. In 1973, the United States repurposed a modified third stage of the Saturn V rocket, launching it into Earth's orbit. But this was no ordinary stage. It had been transformed into our first space station. Inside this remarkable space station, astronauts found more than just engines and fuel tanks. It was a home among the stars, complete with living quarters and cutting-edge laboratories for extended stays in space. It was powered by the sun, as massive solar panels stretched out to soak in the boundless energy of our celestial neighbor. Yet, even in the cosmos, challenges arise. During the launch, a mishap cost Skylab one of its colossal solar panels. Undeterred, 3 dedicated crews of astronauts called Skylab their home away from home until 1974. The final crew to inhabit this celestial home spent an impressive 84 days in space. The Saturn V, a colossal rocket, could heft an astonishing 117,900 kilograms, 260,000 pounds into low Earth orbit. It was also the trusty steed that ferried astronauts to the moon, carrying 40,800 kilograms, 90,000 pounds of hope and dreams. But sometimes a smaller Saturn was needed. Saturn IB, a slightly more modest rocket standing at 68 meters, 224 feet tall. To prepare for liftoff, it required a scaffold platform affectionately known as the milk stool. This unique contraption allowed the Saturn IB to match up perfectly with the launch structure's swing arms. The Saturn IB played a crucial role in early Apollo missions, housed the brave crews of Skylab, and in 1975, joined hands with our Soviet friends in the historic Apollo-Soyuz mission. Rockets aren't just confined to Earth's orbit, they have reached far beyond our celestial neighborhood. The Titan rockets, spanning from 1959 to 2005, took center stage for the Gemini missions. These versatile rockets later found their calling in launching unmanned missions, carrying their precious cargo into the boundless depths of space. Upgraded Titan rockets became the stalwarts of interplanetary exploration. They ushered in the era of the Vikings, sending missions to unravel the mysteries of Mars. And let's not forget the legendary Voyager missions that embarked on a grand tour of the outer planets and ventured into the uncharted waters of interstellar space. These titans of the cosmos have left an indelible mark on our quest to understand the universe. Rockets come in all sizes, and sometimes smaller is better. Meet the Canadian-designed Black Brant, a true workhorse of the skies since 1961. This trusty rocket has completed over 800 successful flights, carrying a wide array of small payloads like cameras, instruments, and microgravity experiments. Researchers cherish the Black Brant for its reliability and cost-effectiveness. Some of the larger multi-stage Black Brants boast payload capacities of around 100 kilograms, 220 pounds, and can soar to heights of up to 900 kilometers, 560 miles. Now, let's shift our gaze to the American Delta rocket, a true icon in the realm of commercial and military payload launches. With roots dating back to the early 1960s, the Delta rocket showcases its versatility through various configurations, featuring multiple stages and hefty strap-on boosters that boost its payload capacity to high orbits. Remarkably, the Delta family has completed more than 325 launches, boasting a staggering success rate of over 95%. As we journey deeper into the world of rockets, we encounter the Atlas, a rocket with a rich history. Originating as a missile in the 1950s, the Atlas was transformed to carry the pioneering Mercury astronauts, including the legendary John Glenn, into the cosmos. Over the years, it has played a crucial role in launching a multitude of missions, ranging from commercial and scientific satellite deployments to daring interplanetary voyages. Meet the Atlas V, a powerhouse among rockets. It's the latest descendant of a long line of rockets that have shaped the way we reach for the stars. With its sleek design and robust capabilities, the Atlas V is a true marvel of modern engineering. Its roots trace back to the very beginning of the space age, and today it stands as a reliable workhorse, launching a diverse array of payloads into the great beyond. Imagine a rocket with wings, much like the mythical Pegasus. This is the Pegasus launch vehicle. It takes to the skies, rising to an altitude of around 12,000 meters before being air-launched from beneath the wing of a specially designed carrier aircraft. This innovative approach keeps costs down, making it a preferred choice for launching smaller payloads into orbit. The Pegasus, like its legendary namesake, soars gracefully through the heavens, delivering payloads to their celestial destinations. And the next innovation was the Space Shuttle, a game-changer in space travel. It was a radical departure from traditional rockets. The shuttle consisted of a central external tank, flanked by two solid rocket boosters and a winged orbiter. However, it's essential to note that only the orbiter, a versatile spacecraft that doubled as an airplane and a space truck, made it into orbit. The orbiter was designed with reusability in mind, as were the solid rocket boosters. But each mission required a fresh external tank, a testament to the shuttle's unique design. What set the Space Shuttle apart was its cavernous payload bay, a space brimming with possibilities. Within its walls, it carried science laboratories, space probes, telescopes, and Earth-sensing systems. Some of its most critical payloads were components destined for the International Space Station, our orbiting outpost in the cosmos. The shuttle's versatility knew no bounds. The Space Shuttle program spanned an incredible 3 decades, from its maiden flight in 1981 to its final mission in 2011. In those years, it forever altered the landscape of space exploration. With a total of 135 missions under its belt, the shuttle program was a testament to human ingenuity and determination. As the shuttle era came to a close, it paved the way for new innovations in space travel. The lessons learned from this remarkable program continue to guide us as we venture further into the cosmos. While the iconic shuttles themselves have been retired, their legacy lives on in the dreams of those who aim to reach even greater heights. NASA's Space Launch System, or SLS, is a true marvel of modern engineering. SLS represents a new era of human exploration, designed to venture beyond Earth's orbit. With unmatched power and capabilities, it stands as the sole rocket capable of ferrying astronauts, payloads, and the Orion spacecraft to the Moon in a single mission. The maiden voyage of SLS, known as Artemis 1, marked a historic milestone. This uncrewed flight test integrated the Orion spacecraft, SLS rocket, and ground systems at the Kennedy Space Center in Cape Canaveral, Florida. It laid the foundation for future deep space exploration. Moving on to private endeavors, the Dragon spacecraft takes center stage. Developed by Space Exploration Technologies, or SpaceX, Dragon holds the distinction of being the first orbital spacecraft launched and recovered by a private company. Imagine Dragon as your reliable delivery service to space. It's like a high-tech space truck shuttling payloads and astronauts to and from the International Space Station. The Dragon's trusty companion in this cosmic endeavor is the Falcon rocket family, also crafted by SpaceX. Among them, the Falcon Heavy stands tall, capable of lifting a whopping 64,000 kilograms to low Earth orbit, making it the mightiest U.S. rocket next to NASA's SLS. And now, a smaller yet equally significant player in our story, Sierra Nevada Corporation's Dream Chaser, chosen by NASA for cargo delivery, return, and disposal service to the International Space Station. This spaceplane fleet is a game-changer. Meet Dream Chaser Tenacity, the orbital workhorse, making multiple trips to the space station. It's like your neighborhood delivery truck, ensuring critical supplies like food, water, and science experiments reach their cosmic destination. Now let's take a leap into the world of space tourism, a dream once reserved for the elite, but now becoming accessible to all. In 2004, Spaceship One made history by becoming the first privately developed space vehicle to carry a pilot beyond 100 kilometers, and it won the $10 million Ansari X Prize. Imagine soaring above the Earth's atmosphere in Spaceship Two, the next-gen version. Thanks to visionaries like Burt Rutan and Microsoft co-founder Paul Allen, the dream of spaceflight is becoming a reality for tourists and researchers alike. These remarkable journeys into space will soon originate from Spaceport America in New Mexico, ushering in a new era of space travel. In the vast expanse of space, a new era is dawning. Private spaceflight companies are leading the charge, revolutionizing rocket launch technology and making the cosmos more accessible than ever before. At the forefront of this transformative journey stands SpaceX, a company founded by the visionary entrepreneur Elon Musk. SpaceX has etched its name in the annals of aerospace history by introducing the world to something truly groundbreaking: the orbital-class reusable rocket. Picture this: a massive rocket, the Falcon 9, soars into the sky, carrying precious cargo. But what sets it apart is what happens next. After fulfilling its mission, the Falcon 9's booster doesn't fall into the abyss of space debris. Instead, it autonomously returns to Earth, landing gracefully on a designated pad. On December 21, 2015, SpaceX made history when they successfully landed one of their Falcon 9 boosters during an orbital launch. This achievement was a game-changer. It marked the dawn of a new era in spaceflight. On December 21, 2015, SpaceX made history when they successfully landed one of their Falcon 9 boosters during an orbital launch. This achievement was a game-changer. It marked the dawn of a new era in spaceflight. No longer were rockets destined to be single-use vehicles, leaving costly debris littered in Earth's orbit. SpaceX's innovation brought the concept of reusability to the forefront. The Falcon 9, the primary orbital rocket used by NASA, is a marvel of engineering. It comprises two main stages: the first stage, responsible for the initial liftoff and ascent, and the second stage, which carries the payload into orbit. The first stage of the Falcon 9 is equipped with a cluster of 9 Merlin engines. These engines are powered by a combination of liquid oxygen and rocket-grade kerosene, commonly known as RP-1. This potent mixture propels the rocket into the skies with incredible force. The Merlin engines are not just powerful, they are also reliable, making the Falcon 9 a workhorse of modern spaceflight. But what truly sets this rocket apart is its ability to return to Earth intact. As the Falcon 9's first stage separates from the second stage, it doesn't become space junk. Instead, it performs a controlled descent, using its grid fans to steer and its engines to slow down. This controlled descent is a feat of precision engineering. Upon reaching the designated landing pad, the Falcon 9 booster touches down gently, like a bird returning to its nest. It's a remarkable sight, one that symbolizes a sustainable future for space exploration. But SpaceX's journey doesn't end there. They have not only redefined rocket technology, but also introduced a new era in human spaceflight. The Falcon 9 carries astronauts to the International Space Station, nestled inside the Dragon capsule. This state-of-the-art spacecraft ensures safe and comfortable journeys to the cosmos for our astronauts. The Dragon capsule's reliability has made it an integral part of NASA's plans for human space exploration. Thanks to SpaceX's groundbreaking innovations, space has become more accessible than ever before. But why is reusability so crucial for the future of spaceflight? The answer lies in economics and sustainability. Reusable rockets reduce the cost of space launches. Imagine building a new car for every road trip. It's neither practical nor environmentally friendly. The same goes for rockets. Reusability minimizes waste and maximizes efficiency. Additionally, reusability opens the doors of space to more people. By making launches more affordable, we empower scientists, researchers, and explorers from around the world to reach for the stars. This democratization of space is not just a dream, but a tangible reality, thanks to SpaceX's relentless pursuit of innovation. Despite facing challenges in the early days, SpaceX has conquered the world of reusable launch technology, aiming to reach incredible destinations like Mars, the Moon, and beyond. The company's unwavering commitment to innovation has given birth to the Starship, a next-generation reusable rocket designed to become the most potent launch vehicle ever created. The significance of the Starship goes beyond its sheer power. It represents the promise of sustainability in space exploration. Imagine being able to use the same rocket up to 1,000 times. It's not just a rocket, it's a step towards a more sustainable way of exploring space. Powering this celestial journey is SpaceX's choice of fuel, methane. Derived from capturing natural methane sources, this renewable fuel not only reduces our dependence on traditional fossil fuels, but also offers significant cost savings and better performance. As we explore the stars, sustainability becomes our guiding principle. The Starship's prototypes are powered by SpaceX's innovative methane-fueled Raptor engines, embodying the company's vision of pioneering solutions. Other private spaceflight companies have followed suit, recognizing the potential of methane in propelling humanity into space. To understand SpaceX's accomplishments, let's take a journey through the extensive history of rocket launch systems. From the visionary Robert Goddard, who kickstarted modern spaceflight, to the present day where SpaceX pushes the boundaries of what's possible, each step forward builds on the last. Considering these humble beginnings is truly awe-inspiring. Failures and successes, and an unwavering human spirit have propelled us to this remarkable moment in space exploration. Fast forward to 2021, when SpaceX achieved another milestone, the launch of the first all-civilian crew aboard the Dragon capsule. This marked a turning point, showing that space travel is not just for astronauts. These brave individuals are the pioneers of a new era, where space is not limited to a select few, but open to anyone with a dream and the courage to pursue it. On July 1, 2023, the European Space Agency, ESA, sent its Euclid satellite into space. It hitched a ride on a Falcon 9 rocket, heading to a special spot near the Sun and Earth. The satellite's mission? To observe distant galaxies and learn more about dark matter and dark energy. JAXA, Japan's space agency, had its own impressive launch on September 6th. They sent up the XRISM X-ray Space Telescope and a lunar lander called SLIM. Moving further into our solar system, on September 2nd, ISRO, the Indian Space Research Organization, launched Aditya L1. Its mission is to study our closest star, the Sun. Back in April, ESA made waves when they launched the Jupiter Icy Moons Explorer, JUICE spacecraft. This ambitious mission aims to explore Jupiter and its large ice-covered moons after an 8-year journey. ISRO continued its lunar exploration journey with Chandrayaan-3, which took off on July 14, 2023. It included a lander, a rover, and a propulsion module, and successfully landed in the Moon's South Pole region on August 23, 2023. Russia also ventured to the Moon with its Luna 25 lunar lander, launched on August 10, 2023. It marked Russia's first attempt to land on the Moon since 1974, although it faced technical glitches and ended up crashing on the Moon on August 19th. JAXA wasn't done yet. On September 6th, they launched the Smart Lander for Investigating Moon, SLIM lunar lander, which carried a mini rover along with a space telescope called XRISM. Back on Earth, the OSIRIS-REx mission returned on September 24th, with precious samples collected from the asteroid Bennu. In the realm of human spaceflight, we witnessed a new record on May 25, 2023. An astounding 20 people were in space at the same time. 11 were on the International Space Station, ISS, 3 were on China's Tiangong, and 6 were aboard the VSS Unity suborbital spaceplane. Just 5 days later, on May 30th, another record was broken with 17 people simultaneously orbiting Earth. Space tourism had its moment with Axiom Mission 2, a private crew mission to the International Space Station launched on May 21, 2023, using a SpaceX Falcon 9. The crew returned safely to Earth on May 31, 2023. Virgin Galactic made headlines with its Unity 25 mission on May 25, 2023. This marked the first mission for Virgin Galactic's suborbital spaceplane, VSS Unity, since 2021. Virgin Galactic continued its streak with the Galactic 01 mission on June 29, 2023, and Galactic 02 on August 10, 2023, carrying the first space tourist. Galactic 03 followed on September 8th. In the field of rocketry, there were notable milestones and challenges. The maiden flight of the United Launch Alliance's Vulcan Centaur is planned for 2023 alongside other smaller rockets. ABL Space Systems RS-1 had its debut flight on January 10th, but unfortunately failed to reach orbit. On March 7th, JAXA/MHI H3's maiden flight faced difficulties when the second stage failed to ignite, leading to the loss of the ALOS-3 land observation satellite. Relativity Space made strides with its Terran 1 rocket, showcasing the viability of 3D printing for major structural components. However, it faced a setback when the second stage failed to ignite after stage separation, leading to the retirement of the rocket in favor of developing the Terran R vehicle. On April 2nd, Space Pioneer's Tianlong-2 successfully reached orbit, marking the first successful launch of a Chinese privately funded liquid-fueled rocket. SpaceX's Starship had its inaugural test flight on April 20th, aiming to orbit Earth. Although some engine issues arose, it showcased the potential of this innovative spacecraft. In April, Evolution Space conducted its first space flight test with the Gold Chain Cowboy solid-fueled rocket. Virgin Orbit faced financial challenges and declared Chapter 11 bankruptcy on April 4, 2023, resulting in the retirement of the Launcher 1 rocket. On May 30th, North Korea attempted its first orbital launch with the Cholima-1, carrying the military reconnaissance satellite Malagyeong-1. Unfortunately, the launch failed to achieve orbit due to early ignition of the second stage, leading to a crash into the Yellow Sea. On July 5th, Arianespace's Ariane 5 rocket completed its final mission. On July 12th, Landspace's Zhuk 2 rocket made history by becoming the world's first methane-fueled rocket to successfully reach orbit. On August 2nd, the Antares 230+ rocket completed its final mission. On September 5th, the sea-launched version of the Series 1 launch vehicle, designated Series 1S, had a successful debut. SpaceX's Falcon family of rockets set a new yearly record for launch attempts on September 16, 2023. Turning to satellite technology, on January 27th, ESA reported a successful demonstration of a braking sail-based satellite deorbiter named ADEO, which could aid in space debris mitigation. In April, Chinese media reported tests of flexible organic solar cells on balloons in the stratosphere, offering potential applications in renewable energy. On July 29th, a Falcon Heavy rocket launched the Jupiter 3 EchoStar 24 communications satellite to geosynchronous orbit. This satellite, with a mass of over 9 tons, became the heaviest geostationary satellite ever launched. On June 1st, Caltech achieved a significant milestone by demonstrating solar energy generation from space through its SSPD-1 spacecraft. These remarkable developments in space exploration and satellite technology continue to shape our understanding of the cosmos and our capabilities in outer space. While NASA has plans to launch the Psyche spacecraft in October 2023, this orbiter mission will delve into the origins of planetary cores by studying the metallic asteroid 16 Psyche, and it will ride into space on a Falcon Heavy launch vehicle. Looking ahead, the next 2 decades hold the promise of humanity finally setting foot on Mars. The Moon, once a distant neighbor, is now within reach. SpaceX's vision extends beyond Earth, sparking curiosity that will drive us to explore these celestial destinations. As we dream of walking on alien landscapes and gazing at Earth from the surface of Mars, the advancements in rocket technology become the wings that carry us towards these celestial dreams. The evolution of rocketry hints at possibilities beyond conventional propulsion. Nuclear propulsion and light propulsion stand on the horizon, exciting prospects that could launch humanity into the far reaches of the cosmos. The stars, once distant specks of light in the night sky, now call us to reach out and touch them. As we stand at the threshold of a new era, let's marvel at how far we've come and dare to dream of the endless possibilities awaiting us. Don't forget to like and subscribe to our channel. Stay tuned for more.